Hello everyone. Today we are going to see what is Atomspace in MeTTa and also how we can use Atomspace for querying informations or knowledge from the Atomspace. And also we are going to see about types that we have in MeTTa, which are the 4 types that we are going to see. So today we start with what is Atomspace. So Atomspace is an experiment or a software that's been part of the open code, or what we call it the Hyperon software structure. So it is mainly a knowledge-based representation that comes with how we can store knowledge or data or practice in the Atomspace, and also how we can query with it. So Atomspace is, or simply space is anything that we can add any form of knowledge or any form of representation or facts that we have in the Atomspace or in the space, then it comes up with its query language, which is what we are going to see it later on. So Atomspace comes with 2 features. One is how we can represent our data. The next thing is also how we can access that data and also modify it. So this is what Hyperon comes up with Atomspace. So the next thing is what types that we have in Hyperon or in MeTTa. So in MeTTa we have 4 types. The first one is a symbol. So symbol is we can think of it as a simple representation of characters or Unicode characters that can represent facts as simple as it is. So you can think of it as a single letter or a combination of characters like that. So such kind of representation of data we have symbolic type in our MeTTa representation. And the next one is expression. So when it comes to expression, expression is anything that can encapsulate or wraps other atoms. For example, if we define a name or a simple name, for example, we say Adam, and we encapsulate or wrap it into parentheses, it would have a type of an expression. So expression is the second type that we have in MeTTa. And the third one is variable. So as we know in other programming language, variable is anything that can store anything that we are going to assign on it. So in MeTTa we start defining variables using $sign, and there is a variable name. So we start with a $sign and any variable name. Such kind of representation would have variable types. So we would see how we can access or how we can check the types of defined atom using a simple query as well. And the last one is, which is the 4th type in MeTTa, is called grounded. So we have these grounded atoms. So grounded is anything that can reduce what is passed through it. So we have built-in functions like match and others that we are going to see them on the coming sessions. So such kind of definitions or such kind of functions would have grounded type by default. And besides that, also we have numbers as grounded type, we have expressions as grounded type. So such kind of representations would have grounded type. So to recap, in MeTTa we have 4 types. The first one is a symbol. So symbol means anything which is a combination of Unicode characters or simply characters. So if I say letter A, by default it would have a symbol type. So such kind of representations will have symbol MeTTa type. The second one is we have shown is an expression. So an expression is anything that wraps an atom, right? So if I have a symbol and if I wrap it with an parenthesis or like that, it would have an expression symbol, an expression type as well. So the second one is the variables. So the variables is any definition that start with $sign and variable name, which we use in different other languages like as Python or other programming language. We have the types called variables, right? So that's the same in MeTTa as well. So variables are the ones that we are going to use to store data that we are going to assign on them. And the last one is grounded type. So grounded type are numbers or strings. Such kind of definitions would have a type of grounded type. And we can also have functions as grounded type. For example, simple arithmetic operation, which is addition, a plus sign, would have a grounded operation because it accepts arguments and reduce or do some operation on it. So these are the types, fourth kind of type in MeTTa. The other one is how we represent data in Atomspace, or representation of knowledge in the Atomspace. So since we have an enormous or huge amount of data or huge amount of knowledge, how can we able to represent that in the Atomspace? So the one thing that Atomspace comes in handy is that we can represent our data as whatever we want, right? So for example, here we are seeing how we can represent family tree representation, right? For example, if we have two persons and they have a relationship like parent-child relationship, how can we represent that into the Atomspace? So this is a simple example of how we can represent factors or knowledge in the Atomspace. For example, we can say Adam is a parent of Bob. So such kind of simple definitions can express our knowledge in the Atomspace. And later on, we also going to see how we can access or retrieve the knowledge that we have added in the Atomspace. So when it comes to representation of knowledge, we are the one who's going to decide in what format we are going to store in the Atomspace. So the things, for example, the names would be nodes, and the types or the relationship between them would be represented as a link, right? For example, the ones that we used earlier, we said that Adam is a parent of Bob, right? So Adam and Bob would be nodes in our Atomspace, and parent relationship would be a link, right? So using that link, we can infer that the person Adam is actually the parent of Bob, right? So using that kind of representation, we can add any form of data into the Atomspace. We can see also how we can retrieve the data we have added into the Atomspace, and also how we can modify it in the coming sessions as well. The next one is where the core operations comes in Atomspace, which is matching, right? So we have some kind of knowledge representation, how we can access data, or how we can do the queries, right? That's where the core operation comes in MeTTa. So in MeTTa we have a built-in function called match. So match would accept three parameters. So match accepts three parameters. The first one is the space, where we are going to query, or where we are going to search for knowledge, right? So that specify which space are we looking at. So we have a placeholder or parameter for that. And the second one is pattern, right? So what are we looking for? What kind of knowledge are we looking for? Since we represent huge amount of data in the Atomspace, so what specific knowledge am I looking at right now? So that thing is covered in the pattern section, right? And the third one is the output pattern. So what am I going to do after finding such knowledge or such fact? For example, I'm searching for the parent of Bob, which is Adam, I have defined earlier, right? So what am I going to do with that? Should I return the name of the parent, or should I do any other operation? So that's going to be specified here in the output pattern. So match always requires three arguments. The first one is the space where we are looking for that specific data, and the second one is what kind of data are we looking for, which is the pattern, and the third one is the output pattern, or the output that we are going to return. So as you can see from here, guys, we have match definition with 3 parameters to retrieve the name of person, right? The parent of specific person, which is Bob, right? So we can write such kind of queries in the meta, so that it's going to return us the fact that's been stored in the Atomspace. As we can see earlier in the previous slide here, we have defined 2 parents of Bob, right? So one we have defined is Tom. Tom is the parent of Bob. So we have defined it here, and also we have also add other knowledge or other factors. For example, Bob is also the parent of Anna. So we have kind of trying to define such kind of relations. Then when it comes to accessing or retrieving the data, for example, we are trying to access the parent of Bob here, right? So we don't know about how the knowledge is stored. If we have, for example, huge amount of data stored in our Atomspace, we don't specifically know who is the parent of Bob, right? So the thing that we are going to do is using a match, which is a cooperation in MeTTa, and we are going to specify the space where we are looking at, and also what kind of pattern am I looking at. Then we would specify the return type. So in this case, we are saying that match this kind of knowledge, which is represented as parent, someone, and Bob. So we are trying to find who is X or who is parent of Bob. Then after that, the third argument is the return type. So we would say return the parent of Bob. Then we would get the results from the matched space, right? Just to give you highlight about what we did, since I have defined such family tree representation in my code base, as you can see, I have created a file called example.meta, and I have specified simple family tree relationship where these kind of representations are specifying the genders of a person. For example, for Tom, I'm saying is a male. For Anna, I'm saying female, and so on. And for Adam, I'm saying male also. So I'm defining such kind of knowledge in the Atomspace. And besides that, I'm also defining the relationship between these persons, right? So, for example, Bob has a parent called Tom. So I also defined here. So using such kind of representation. As we said earlier, the name of the persons would be the nodes, right? And the relationship between them would be a link, so that we can traverse or we can match such knowledge using the links in the nodes. So here we have defined the 2 child of Toms, which are Bob and Liz. So I have defined both of them here. If I try to run the first match code, it would return what? Tom, right? So as you can see here from the console, I'm getting Tom because whenever I'm specifying and I'm searching for the parent of Bob, it would return the parent as Tom because I have defined such knowledge in my Atomspace, right? So when it comes to defining match, we always have to follow such rule, right? So we have said it accepts 3 arguments. The first one is the space. So here we are saying self. So self means specifying we are looking on this current directory or on the current working file or the current working space. So we are saying, or we are telling to the match that you should have to look such kind of pattern definition only from the current working space, not from other modules or other parts, right? We are going to see them how we can access knowledge that we define in another module in the coming sessions. But for now, we are going to see how we can access factors or knowledge that we have represented on the current working space. So this knowledge that you are seeing here or the family representation, family tree representation, all are exist in self because they are defined here in this working space. Then using that definition, using self, which is telling the match to look it only on the current space, then the second parameter is the pattern, right? So what am I looking for? So that it's this one specify what am I looking for. For now, I'm looking for the parent of Bob. I can say the parent of Liz. I could also get the same because I have defined the same name for the same parent for Bob and Liz, right? Then the last one is output pattern. So what am I going to return? For now, I'm returning the name of the pattern only. I can say any return type as well. I can return string or other information as if such kind of pattern exists. If such kind of definition or such kind of pattern doesn't exist in my Atomspace definition, I would get an empty, right? I don't have such so match would return. I don't see such kind of representation in the Atomspace. So this would return empty if such kind of definition doesn't exist in the Atomspace. But for our case, since we have defined the parents of Bob, this would return Tom as his parent. I hope this is clear. So we can also write to access the parent of Liz using simple query that you have seen here. So the thing that's going to be changed is the persons what we are looking for, right? For the above code, we were seeing for accessing the parent of Bob, right? But what if I want to look for the parent of Liz? I'm just going to modify the name in the parent section, right? In the pattern section, right? So here I'm going to only modify the name that I'm looking for. So if I run this code, I would get Tom for both of them because the parent of Bob is defined as Tom and the parent of Liz is defined as Tom also. So this would be the output of this query. So I have defined knowledge here, as you can see from the screens. Then whenever I'm trying to query that space, the power of match comes in and it gives me capability to search in any space any kind of patterns that I have defined, and it would return if it find if such kind of pattern that exists in my Atomspace. So this is how we can write a simple match query. Then we can retrieve or we can access the knowledge that we have added or that we have represented in the Atomspace. So this is a simple explanation of how we can represent or how we can retrieve data, all right? So what if we want to access a nested representation? For example, what if I want to access the grandparents of a person, right? So how am I going to do that? This is where the nesting matching comes in, right? So using a nested match, we can do any recursive matching as well if our data is not being represented as a simple node-to-node relationship by a simple link, right? For example, if I want to go to different places, I need to pass to different roads, right, or different sites. So using that as a scenario, whenever I'm trying to search knowledge, but that knowledge is represented in nested form, we need to write a nested match so that it can traverse and access that data based on our representation. So whenever I'm trying to do such kind of nested operations, I need to specify what I'm looking for and the return type as well. So from similar to the previous explanation, we have start with match, and match always accepts two arguments. There's three arguments. The first one is the space where we are looking for, and the second one is the pattern. So what kind of pattern am I looking for, then the last one would be the return type, right? The return pattern. So when it comes to nested matching, since our data is not explicitly defined by a single relation, just like we seen earlier, just like Bob is the child of Tom, or Tom is the parent of Bob, such kind of representation are simple or one-level hierarchy, right? But what if our knowledge represented in some form of hierarchy, or some form of recursion, or what we call a nested representation, right? So how we can retrieve such data from the Atomspace. So for that we have an option called match with comma. So match with comma, we can specify what kind of pattern am I looking for. If we are looking for nested operations, right? Okay. So whenever we need to retrieve a nested represented data, or whenever we have a nested matching, so what we are going to do is we need to specify what kind of patterns should be fulfilled before the return time. As you can see here from guys, we have 3 patterns should be fulfilled before returning any data, right? So the first thing is I'm looking for a specific person which is represented using such kind of representation or such kind of pattern. Then this thing should also fulfill such kind of pattern, and also at the last it should be a female. I define the pattern as this. So the match is going to return for me if that query fulfills all of the defined patterns after comma, right? So if I define 3 or 4, as many as you can, as many as you want, then as long as there is a data that, as long as there is a pattern that satisfies such kind of representation, is going to be returned, right? Let's see it with an example so that it would be easier for you. For from the above family tree representation, we have defined the genders of the persons and also their link or their relation, right? So I have defined 2 siblings, which are Bob and Liz. Then I am also defining their genders, right? For Bob I have defined it's male, and for Liz I have defined as she's a female. Then I have this kind of knowledge representation. Now what I'm going to do if I want to retrieve the sibling of Bob, right? From this representation I can write match and do query to give me the siblings of or the sister of Bob, right? So I have this code right here. So it says, as we said earlier, its first argument is the space. So the space is telling where to look the parent I'm going to give for match. So self always refers to the current working space. So it's only look for knowledge which is represented here in this file. Then after that, after comma here, I'm going to define all the patterns that the knowledge should fulfill, right, before it's going to be returned. So the first thing is I need to find, since I'm looking for the sister of Bob. So the first thing is I need to find their parents, right? I need to find the parents of Bob. So to do that, I have such kind of pattern that we also used in our previous example here. So I have defined, first I need to retrieve the parent of Bob, which is I'm going to store it in variable y here. So variable y would store the parent of what? Bob, exactly. So Bob would store y would store the parent of Bob, which is Tom by default, right? So we have defined it here. So it would the variable y would store the value what? Tom, exactly. So after that, we are going to search every child of Bob. So since we retrieve the parent of Bob, I have now the parent's information stored in variable y. Now what we are going to do is I'm going to look for other child Tom have, right? So the parent of Bob is Tom. Then next I'm going to look for, does Tom have any other child other than Tom? So that's what Z is going to store for me, right? So Z is going to store any other child if we define for Tom. Then using that we can have other childs of Tom. Then using that I'm also like defining one pattern here, right? I'm saying that person should be female, right? If I have defined other person, for example, if Bob have another brother, such parent would be failed, such pattern would be failed and is not going to pass, right? So I'm only looking for a sister, so their gender should be, the gender of the person should be female. Then later on at the last we're going to specify the return type, so the return type would be the name of the sister. So let's run this out. So if I first comment the above codes, and if I run MeTTa in the file name, I would get this as defined in the knowledge space. So here what we are trying to do is how we can define a nested pattern, or how we can retrieve information that's represented with using set of links, right? Not just only one single representation or one single link type. So using such kind of definition in merge, we can do much complex operation as well. In the coming sessions, we are going to see how we can also use and extend such nested operation to very complex knowledge representations, and how we can retrieve or get information from the space, even if the knowledge is represented in complex way. So that would be our next sessions. Thank you for your time.